In this video, we're going to talk about inferences about two means. When we say inferences, that means we're going to be doing a hypothesis test, and then we're also going to be constructing a confidence interval, both based on the same problem. When we talk about two means, in this case, we're talking about independent samples. There are also mean problems that involve dependent samples, and we'll talk about those in a separate video. In Chapter 7 and 8, the confidence intervals and hypothesis tests we have learned about involve taking one sample and from that one sample learning something about the one population that one sample came from. In Chapter 9 of the Triola text, we learned about confidence intervals and hypothesis tests involving two samples, each sample from a different population. Our whole focus here is learning about the differences between those two populations. There are always differences between the two samples. The question we have to answer is whether the differences between the samples are big enough for us to conclude that the populations are also different. Chapter 9 addresses three different two-sample situations. Number one, determining if there are differences between two population proportions, and I have a video on that. Number two, determining if there are differences between two population means, and that is the subject of this video. Number three, determining if there are differences between matched pairs. There will be another video covering that. And those matched pairs are also sometimes called means-dependent samples. So some of the terminology gets a little confusing, but this number two type is sometimes called means-independent samples, and number three is sometimes called means-dependent samples, though it's also often just known as matched pairs. We're going to go look at my outline for a minute, and you can see where to find these in the outline. So here's page 7 of the outline. You'll notice right here it says Chapter 9, Inferences from Two Samples. The first box here, all this, well, it's not the whole, that's the whole thing. This first box, this part in here is about proportions. This middle box is means independent samples, and that's what this video is about. The third box is the discussion of matched pairs. So you can find all this stuff at page 7 of the outline. Okay, so let's go a little deeper into this hypothesis test of two means independent samples. Let's start with a notation. In every problem, we are starting with information about two samples. We can refer to them as sample 1 and sample 2. For each sample, we will have the sample size, that's n, the sample mean, that's x bar, and the sample standard deviation, that's s. And I really encourage you, when you have a problem, write it up just like this. Sample 1, sample 2, the sample size of sample 1 is n1, the sample size of sample 2 is n2, and so on. Here's the sample mean of sample 1, the sample mean of sample 2, and the same with the standard deviations. So how about our hypotheses? Like all hypothesis tests, we will need a null hypothesis and an alternative hypothesis. The null hypothesis is always the same for these kinds of problems. It is that the two population means are the same or are equal to each other. So we write this HO mu1 equals mu2. And notice, and I always make a point of this, the hypotheses focus on the population. So mu is the symbol for the population mean. The sample data are about the sample. So x bar is the sample mean, mu is the population mean. But this one here and this one here mean that these are going to relate to the same group, whatever it is. The only difference is this is a sample of that group and this is the population of that group. So again, HO is always the same. Mu1 equals mu2. The alternative hypothesis can be any of the following depending on what the claim is. Mu1 is greater than mu2, mu1 is less than mu2, or mu1 does not equal mu2. So let's do a problem. This problem is called cigarette tar. And I suggest that you pause the video at this point and take a few minutes to read this over and get an idea of what's going on. So I'm going to assume that you have paused the video and read all this stuff, and we're now going to go down to where it says understand the problem. Look at the highlighted words. Test the claim, you see those words right there, tells us that this is a hypothesis test. Mean, and you see that right there, tells us that it will be a hypothesis test for a mean and not for a proportion. Greater than tells us what our alternative hypothesis will look like. And you have to realize that the problem is talking about two different samples, the unfiltered king size group and the filtered 100 millimeter group, which means that we have to approach it as a two-sample problem. And if you just look for a couple of minutes, you'll see it's giving you information about two different groups, how big the group is, what the mean is, what the standard deviation. And then they do that twice. That means there's two different groups. So finally, the phrase greater than, you see that right here, tells us what our alternative hypothesis is going to look like. So as with all hypothesis tests, I use a checklist. And here's the checklist that I use. You can also find it in on page 6 of my outline in the upper right-hand corner. The claim, the hypotheses, the sample data, and alpha. Once you have all these, you can go to your calculator and go through the steps. Your calculator will give you the test statistic and it will give you the p-value. And then once you have those things, you can get to your conclusions, your decision about the null hypothesis, and then after you have that, you can reach your conclusion about the claim. So you see up here, one of the items on our checklist is sample data. So what are our sample data? In these questions, we always have two samples, so set up your sample data like this. Sample 1, and right next to it sample 2. Here you have sample size, the sample mean, and the sample standard deviation. And all of these numbers came right from the problem. Be careful when you put them in. Don't mix up N and X bar and S. Be sure you put them all in the right place. So once you have your sample data listed like this, you can go to the checklist and check off sample data. Now, what is the claim? If we go back and look at the problem, the claim is that unfiltered king-size cigarettes have a mean tar content greater than that of filtered 100 millimeter cigarettes. We must convert this claim to symbols, but remember, the claim is always about the population, so we must use population symbols, not sample symbols. Remember, these are all sample symbols. I just realized, by the way, I had a little mistake here. That S that you see there said X a minute ago, and that wasn't right. So this is S for standard deviation. So let's get back down here. The mean tar content of unfiltered king-size cigarettes is mu1. This is now the population mean we're talking about. Up here we had the sample mean, but now we're talking about the population mean. The mean tar content of filtered 100 millimeter cigarettes is mu2, just like up here, filtered 100 millimeters. This is the sample of this group. So our claim is that the mean tar content of unfiltered king-size cigarettes is greater than the mean tar content of filtered 100 millimeter cigarettes. So this is what our claim looks like using symbols. Mu1 is greater than mu2. Once we have this, we can go to our checklist and check off claim. And now right under that is hypotheses. So what are our hypotheses? We start with the claim, and I really encourage you, line up everything just like this. It's very important to keep all this straight. Our claim is that mu1 is greater than mu2. HO is always mu1 equals mu2, which means our claim has to live in H1, so we're just going to repeat the claim right down here in H1. Mu1 is greater than mu2. Once we have this, we can go to our checklist and check off hypotheses. If we look back at our checklist, one of the items we have to get is alpha. That's the level of significance. The problem says use a 0.05 significance level. This is alpha. So now we can check off alpha. And now we're ready to go to the calculator. We're going to go to Stat Tests 2 SAMP t-test. So I want you to notice this is a t-test we're using, not a z-test. When we were doing mean problems for one sample, sometimes we used t and sometimes we used z. and that depended on whether we knew the population standard deviation. For all practical purposes in this course, you are never going to know the population standard deviations of these groups, so it's always going to be t-test. The calculator will give you an option for a 2-samp z-test, but you're never going to use it. It's only ever going to be 2-samp t-test. Let's again look at my outline so you can see where this is. Here's the outline. Means independent samples, so this is where we are. Hypothesis tests, so we go across, and here you see it. Calculator 2-sample t-test. So we're going to go over to the calculator now and do that. Stat tests 2-samp t-test. There it is. So I'm going to choose that. And we have to enter our data here. So we're going to have to come back over here and find our data. And there's our data. So x bar 1 is 21.1. So we're going to put that in there. 21.1. Sx1, that's this 3.2. So we're going to put 3.2 right there. And then we're coming down to N1, and that's 25. And now we're ready for the second sample. X bar 2 is 13.2. Sx2, it's the same thing, is 3.7. And N2 is 25. So now we have given the calculator all of the sample data. This mu1 down here, this is where we tell the calculator what the alternative hypothesis, or H1, is. Let's go back and see. H1 is the claim that mu1 is greater than mu2. So we have to come down here and choose greater than. And there it is. So we have chosen mu1 is greater than mu2. And that's what we want to have. Now here's this question that says pooled. 99% of the time, pooling is going to be no. The only time pooling is going to be yes is that rare case where the problem tells you to assume that the standard deviations of the two populations are the same. And in that case, they want you to say yes for pooling. It's very rare. All the rest of the time, pooling is just going to be no. And then we're going to come down here to calculate and hit enter. And here we get our test statistic and our p-value. Those are really the only two things that we care about. So here's our test statistic, and again, because it's a t distribution, our test statistic is a t-value 8.07, rounded to 2 decimal places. And here's our p-value, 9.8 e to the negative 11. That means we take this decimal point right here between the 9 and the 8, and we move it 11 places to the left, which means that gives us decimal point 10 zeros and then the 98. In other words, this is really, really, really close to just 0. So I'm just simply putting it here as 0 plus. So our p-value is 0 plus. Now we can check off the calculator and we're ready to go to our conclusions. So first is our decision about HO, the null hypothesis. And that is that the p-value is less than alpha, so reject HO. Again, the p-value was 0 plus, and alpha, we see up here, was 0.05. So the p-value was less than alpha, so we reject HO. I always say that is the most important rule in the whole course. We're going to take a quick look at my outline so you can see where it says that. If we go back to page 5 of the outline in this little box here, that is the most important rule in the whole course. If the p-value is less than alpha, reject HO. If the p-value is greater than alpha, fail to reject HO. Extremely important. Now we are ready for our final conclusion as to the claim. Remember, the decision just addresses HO, and the conclusion addresses the claim, and you have to do them separately. You have to deal with HO before you can deal with the claim. And let's again take a quick look at the outline to see how we do that. Here we are on page 6 of the outline, and we're up here in this part. So the claim was H1, and we rejected HO. So if the claim is H1, that means we're in this column here. Sorry for that. We're in this column here. We rejected HO. That means we're in this row, and where those two things cross is right here. The sample data support the claim that. So here's our conclusion. The sample data support the claim that, and the rest of this, we just pick up the claim right off of the problem. Unfiltered king-size cigarettes have a mean tar content greater than that of filtered 100 millimeter cigarettes. So we've done the problem, but most instructors would like to see a little more math in coming up with a test statistic. If you remember, the calculator just handed you the test statistic right here, t equals 8.07. The calculator did all the math for you and just gave it to you. Most instructors would like to see a little bit more than that in terms of where that test statistic came from. Here's the generic formula, and then here's how we apply it to this problem. X bar 1 was 21.1. That's right off the sample data. This is the mean of the first sample. This is the mean of the second sample. That's 13.2. Mu1 minus mu2, notice these are now population symbols. And what we do there assumes that the null hypothesis is true. The null hypothesis, if you remember, says that mu1 equals mu2. And if that's the case, then mu1 minus mu2 is going to be 0. So we always can just put a 0 in for that. Down here we have the square root. This is the standard deviation. S1 is the standard deviation of the first sample. S2 is the standard deviation of the second sample. That's what we've put those here, 3.2 and 3.7. Then we have to square those. That will give you the variance of each of those. So that's where these numbers came from. N is just the two sample sizes. Each of them are 25. You work out all this math and you get 8.07, which I believe is the same thing we got from the calculator. Yes, it is. Sometimes you'll have a little rounding error so that the number you get when you use the formula is slightly different from what the calculator gives you. That's a little rounding error and it shouldn't hurt anything. So now we're going to do a confidence interval based on the same problem. Let's start with examining the structure of the confidence interval. And the important thing here is that we are estimating the difference between two population means. And the way we put that difference statement into notation is to say mu1 minus mu2. The mean of the first population minus the mean of the second population is between whatever number goes here and whatever number goes here. And these should look familiar. This is the mean of the first sample. This is the mean of the second sample. Same thing here. The mean of the first sample, the mean of the second sample. The problem gives you those. And then the E stands for the margin of error. In this case, we subtract the margin of error from this. And in this case, we add the margin of error to this. And that's actually how the calculator comes up with the confidence interval that it will give you. So let's do a problem. It's the same problem we did in the hypothesis test. So I'm not going to read it word for word, but I'm going to assume that you're going to pause the video now and read this carefully to remind yourself what kind of sample data they're giving us. And then we're going to look at this down here where it says understand the problem. Look at the highlighted words. Construct a 90% confidence interval. This tells us that this is a confidence interval problem and not a hypothesis test. See the word mean here? That tells us that it will be a confidence interval for a mean and not for a proportion. And again, you have to notice that the problem is talking about two different samples, the unfiltered king-size cigarettes and the filtered 100 millimeter cigarettes. And it says we're estimating the difference between the means of the two populations that the samples come from. All of which means we have to approach this as a two-sample problem. So what are our sample data? Well, they're the same as they were when we did the hypothesis test. We set it up exactly the same way. This is the way you keep everything straight. And notice, very important, the unfiltered king-size cigarettes are sample 1, and the filtered 100 millimeter cigarettes are sample 2. Very important you keep those in mind. Which one is sample 1, which one is sample 2. Let's find the difference between the sample means. Well, The sample mean for the first sample is 21.1. The sample mean for the second sample is 13.2. So the difference in the sample means is 7.9. In other words, the unfiltered king size mean, sample mean, minus the filtered 100 millimeter sample mean equals 7.9. The difference is positive. For that to be true, that means that the first mean has to be bigger than the second mean. That the unfiltered king size mean has to be bigger than the filtered 100 millimeter mean. It's good to do this just to get a flavor for what we're dealing with here. We're now ready to go to the calculator and go to stat tests 2 samp t int. And let me show you again on my outline where this is. Here we are on page 7 of the outline. We're working on means, independent samples. Here, this whole row is hypothesis tests. This row down here is confidence intervals. So here you go. To do a confidence interval for two means, we use 2 samp or sample t int. So here we go. Now we're going to do it on the calculator. Stat tests 2. See, that's 2 samp t test. That's not what we want. We want 2 samp. There's z interval. We're not doing z interval. We're doing t interval. 2 samp t interval. That's where we want to be. So I'm going to click enter. If you'll notice, the calculator remembers all the sample data. That's nice. Our confidence level, I don't remember, so let's go back up and see, is going to be 90%. So we're going to come down here and make this 90%. Again, pooling is going to be no almost all the time for the same reason I talked about when we did the hypothesis test. And then we're going to hit calculate. And here's our answer. This is the confidence interval here, these numbers in parentheses. 6.2584, 9.5416. To state it more completely, the confidence interval says that the difference between these two means, the mean of the first group minus the mean of the second group, if we were to calculate that difference for the whole population, the difference would be somewhere between this number and this number. If we're to state our conclusion in words, we would say we are 90% confident that the true difference between the mean tar content of unfiltered king-size cigarettes and the mean tar content of filtered 100 millimeter cigarettes is between 6.2584 and 9.5416. So let's interpret this a little bit more. It's a bit complicated, so you need to focus. The analysis is just like what we did when we compared the sample means. Look at the complete statement of our conclusion. Mu1 is unfiltered king-sized. Mu2 is filtered 100 millimeters. When we take this one, this mean, and subtract this mean, our answer is somewhere between these two numbers. And here we sort of say this again. When you take the mean tar content of the population of unfiltered king-size cigarettes, here you go, and subtract from that the mean tar content of the population of filtered 100 millimeter cigarettes, that's that, your answer will be somewhere between these two numbers. Notice two things. One, for the difference to be positive, and you'll notice both of these are positive, the mean tar content of the population of unfiltered king-size cigarettes must be higher than the mean tar content of the population of filtered 100 millimeter cigarettes. And two, the low end of our estimate is 6.2584 and the high end of our estimate is 9.5416. In other words, both are positive, which means our estimate of the difference between these two things does not include 0. If our estimate of the difference had included 0, then we would say that there may be no difference between the two populations. So, the fact that these are both positive means that we are 90% sure that the population difference is positive, which means we are 90% sure that the mean tar content of the population of unfiltered king-size cigarettes is higher than the mean tar content of the population of filtered 100 millimeter cigarettes. Or we can state it the other way. We are 90% sure that the mean tar content of the population of filtered 100 millimeter cigarettes is lower than the mean tar content of the population of unfiltered king-size cigarettes. Two different ways of saying exactly the same thing. And notice, this is the same result we got when we did the hypothesis test. Now let's talk about how to find the margin of error. There's an easy way and there's a hard way. The easy way, as with all confidence intervals, is to say that E, the margin of error, equals the high end of the confidence interval minus the low end of the confidence interval divided by 2. And when we do that, we get this, 1.6416. The hard way is a pretty involved formula for calculating the margin of error for two means. And it's fairly involved, and there's good stuff online from other sources that you can go to learn about this, so I'm not going to do it here. Again, there's more than one place to go. I would encourage you to check out the Khan Academy video called Confidence Interval of Difference of Means. And that is the end of this video.